Hello, dear students. Let's see one more example of recurrence relation dividing functions and how to solve these recurrence relations which have dividing function using tree method. In the previous video, we saw an example and how to solve the recurrence relation using tree method. Let's see one more recurrence relation. Tn is equal to 2tn by 2 plus n if n is greater than 1, but Tn is 1 if n is equal to 1. So this given is the base case here, and this is the case where the recursion stops. Now we want to know what is the time complexity of this recurrence relation. So just watch the first equation given Tn is equal to 2Tn by 2 plus n. Now here the right hand side of the recurrence relation contains an additive term n, and one more term to that n is nothing but the function t and multiplied by 2 times. So 2 times tn by 2 plus the additive term n. So we start our tree with that additive term n. This will be the root, n will be the root, and it will have two children. The children will be tn by 2 and tn by 2. Now just check, you read this particular portion of the tree as tn, and tn is nothing but tn by 2. Check what I am taking, tn by 2 plus tn by 2, that is 2tn by 2, isn't it? Plus n. So all these terms, which I have written are getting added. But the additive term, that is n, in the recurrence relation is always shown as the root. And the functional term, that is t is the functional term, isn't it? Is always shown as the child. So we then show the cost of the level. Now, if you see, if you see the root here, we say that first time, n operations are getting done, like that we read. The algorithm performs n operations. So the cost of doing n operations is n, we say. But we can't write the cost of these operations because we don't know what is tn by 2 at both places here. So here comes the point. We will have to know what is tn by 2. The question is, what is the value of tn by 2? Now come to the original equation, Tn is equal to 2 Tn by 2 plus n. We are interested in knowing what is Tn by 2. Then at both places, left hand side and right hand side, instead of n, if we put n by 2, here also at the right hand side, if we put n by 2, we will get the value of Tn by 2. Tn by 2 is 2 Tn by 4 plus at this place also we will have to put n by 2 plus n by 2, isn't it? So this is the value of Tn by 2, correct? Now, can you now understand how this tree which was drawn by us will get extended? Just check, the tree had n as root. It still remains root, and it had two children. I'm not writing those children now, Tn by 2 and Tn by 2, isn't it? But then what is Tn by 2? Tn by 2 is 2 Tn by 4 plus n by 2. Now look at this. This is the additive term, n by 2. So we will write n by 2 is getting added with Tn by 4, Tn by 4. What is this? What is this section? You tell me. This section is Tn by 2, isn't it? Yes. And the left child of this root was Tn by 2. What was the right child of the root? Tn by 2. And what is Tn by 2? Check this. It is n by 2 added with Tn by 4 and Tn by 4. This is nothing but Tn by 2 again. This is Tn by 2, isn't it? So this is the tree that we had root indeed was n, and the two children of root were Tn by 2, n by 2. And we extended the tree. Now what is the cost of the root? Cost of the root is n. And what is the cost of next level, which I am marking here? Check this level. This is n by 2 plus n by 2, which is also n. So we have opened up two levels, and both levels have cost n. Now the question arises, what is this Tn by 4? It is very easy to say that if Tn, the original equation is Tn is 2 Tn by 2 plus n. This was the recurrence relation. We want to know what is Tn by 4. Then at both places, left and right, at each place of n, if we put n by 4, then we will get Tn by 4 here is equal to 2 Tn by 8 plus n by 4, isn't it? So our tree will further extend, isn't it so? The root was n. The two children of the root were n by 2, n by 2, correct? Now the two children of this n by 2 will be n by 4 and n by 4, with each of them representing Tn by 8, Tn by 8, this also Tn by 8 here, two children, Tn by 8. Same goes over here also. It will have two children, n by 4, n by 4, with each of them having Tn by 8 as the child. So assume everywhere Tn by 8 is written. So the cost of the root now will be n. Cost of next level, you watch, is also n. Cost of the next to next level here, n by 4 added 4 times, n by 4 added 4 times is going to be n again. And this tree grows like this. Obviously, at the next point, at each of these places which I am underlining, we will get n by 8 term, n by 8, isn't it? And the two children of that n by 8 will be tn by 16 with tn by 16. And this is how the tree will grow. Now, obviously, this tree should end somewhere. The tree always ends at leaf node. And the leaf will occur only if you get T1. Again, you check this is the base case. Why? Because we know the value of T1. T1 is 1, so it doesn't call any recursive step. So recursion obviously stops when this bracketed term with T is having a value 1. So somehow, these brackets of T, whatever we write in the brackets should converge to 1. Now, can you find out a generic term now? The generic term you can find out here at this level. Here, the level at which we were talking about is T n upon 2 raised to I. Yes, I am sure all of you watching this video have found out that where I is the level number, if you see this level is 0, next level is 1, next level is 2. So this is clearly 2 raised to 2. Check n upon 2 raised to 2 it is. And this level is 3. This is n upon 2 raised to 3, n upon 2 raised to 3, that is n upon 8. So this is the generic term that we have got, which gets generated at each level. And somehow, we want this n upon 2 raised to I to become 1. Hence, we equate n upon 2 raised to I should be 1. This implies n should be 2 raised to I. And this implies that let me erase a few things. This implies that I should be equal to log of n to the base 2. But what is I? I is level number. That means the number of levels that this tree will have till we reach T1. This is what we want to reach, isn't it? T1. The number of levels that the tree will have is exactly log of n to the base 2. And now it is so easy. If the number of levels is log of n to the base 2, check this. Number of levels is equal to log of n to the base 2. And we want to find out total cost, isn't it? We want to find out cost at each level. And we know that cost at each level is exactly n, isn't it so? So obviously cost at each level multiplied by number of levels is going to give us the total cost. So hence the total cost is n into total cost or total number of operations done by the algorithm is n into log of n to the base 2. Hence we can write Tn is equal to big O of n log of n to the base 2. Just don't get confused. We can't drop n. Somebody will say, why don't you drop n and write log of n to the base 2? Maybe this explanation is silly. Well, if it was, suppose if we got something like this, n plus log of n to the base 2, then n is the largest term and there is addition with log of n to the base 2. So we say this is polynomial of degree 1 and we can drop log n and we can write it is big O of log n, isn't it? But here n is getting multiplied with log of n to the base 2. So obviously we will have to keep both the terms, and the analysis or the time complexity of this recurrence relation is big O of n log n to the base 2. Check that whatever we do substitution or tree method, both these methods are difficult. I mean, at times, we get such difficult recurrence relations that finally, it will be very difficult for us to compute the cost at each level. Let me give you an example where suppose we are given a recurrence relation like this. Tn is equal to, let's say, 2 Tn by 4 plus n log n. Just check this, n log n. Now how, and Tn is 1 obviously if n is 1. This is the recurrence relation given. Now it becomes so complex for us to solve it either by substitution method or by tree method. For example, if we use tree method, then Tn will be represented as n log n. Check that, n log n added with Tn by 4 two times. This is nothing but Tn by 4 added with Tn by 4. That's the way how we got 2Tn by 4 here plus n log n. But then we will have to extend Tn by 4. And what will be Tn by 4? Tn by 4 will be equal to, just check, Tn by 4 will be equal to 2Tn by 16 plus n by 4 log of n by 4. Now it becomes complex, isn't it? Because this finally, what will happen is that as we go on extending the tree, check that root is n log n, and the children of this tree root will be n by 4 log n by 4 and n by 4 log n by 4, isn't it? And the two children of each of these will be Tn by 16. N by 16. Now, the cost of this particular level, you see, n log n is n log n. Obviously, if you add all this, you will get n log n. But how are you going to add this? This is going to be n by 4 log n by 4 plus n by 4 log n by 4, which will be nothing but 2 into n by 4, 2 into n by 4 log n by 4. And that will be n by 2 log n by 4. These terms, are very disturbing at times. And then finally, to add all these costs becomes very difficult, and we need some very good understanding of mathematical terms, series, how we may get arithmetic progression, geometric progression, all that. So solving dividing functions using tree method or substitution method is difficult at times. And I agree that I have taken both the examples that I took, were very simple examples. And I did not dare to take difficult examples. Let me clarify. Yes, I did not dare to take difficult examples because there is a good news that there is a master's theorem which we can use to solve recurrence relation, provided the recurrence relation is a dividing function. And we will see how easily we can solve such very complex recurrence relations using Master's theorem in the next video. Thank you very much.